This is an introduction to financial maths, and the key starting point for financial maths is to realise the following, that the value of money is not as straightforward as it seems. And what I mean by that is, for example, if I've got €100 right now and I invest it, well, because of interest, it's worth more in a year's time. So that 100 grows in value. And vice versa. What it's worth in a year's time, if I bring it back to the past, it's worth only 100 again. It decreases in value from its future value. So we can sum up all this by saying the following. If I receive €100 right now, well, because of interest, that will be worth more than 100 in a year's time. And that's called the future value of the money. So future value is a key term from now on as well in financial maths. And vice versa. If somebody gives me €100 in a year's time, and if I bring it back to today's value, it's actually worth less than 100 because we're taking off the interest. So the present value of 100 received in a year's time is less than 100. So we'll illustrate all this with a simple example. So let's take some simple numbers. Invest 500 at a rate of 10%. Now that's not a realistic interest rate, but just let's go with that to get started. So if I invest €500 at an interest rate of 10%, what is the future value of that money in 1 year's time? Well, the first thing you do is you convert the percentage to a decimal. So 10% is 0.1 as a decimal, because now we can use it in a formula. And if we invest the 500, well, the future value of our 500 is the following. Well, it's 1 times the 500, so we get our money back, plus the interest times 500, which is 0.1 times 500. So altogether, that's 1 plus 0.1 times our money, which is 1.1 times 500, which is €550. So we say the future value of the 500 is the 500 multiplied by 1.1, which is 550. We can also rearrange that formula, of course. We could divide across by 1.1. So if you divide the 550 by 1.1, you get the 500. So that's the future value, the 550. So if we divide the future value by the 1.1, we're back to the present value again. So this first formula takes you forward in time. Your 500 becomes 550. And this second formula takes you backwards in time. Your 550 in the future is only worth 500 now. It's the same formula, just written in two different ways, depending on what you're looking for, future value or present value. Now we can generalize these formulas by calling the interest rate I. So that means that, in general, the present value of your money, what's the future value? Well, it's 1 times your money plus the interest times your money. So it's 1 plus I times the present value gives you the future value. And once again, we can rearrange this formula. We can divide across by 1 plus I, and we get present value is future value over 1 plus I here. Or we can just shorten it to F equals P into 1 plus I, where F is final value or future value, and P is the present value of your money. And here it is again rearranged. If you have the future value and you divide by 1 plus I, you're back to the present value. Now we can generalize this formula. That's for 1 year, let's say. Let's say that's 1 plus I is your future value after 1 year. Well, let's see what it is after 2 years. So down here, again, starting off again, we started off with P. That was our present value on the first day of the first year. After 1 year, it amounted to 1 times your money plus I times your money. So that's 1 plus I times P. So at the end of the first year, your money has amounted to P into 1 plus I, which I've highlighted in red here. Of course, that's now your starting amount for the second year. So let's start off again for the second year. So what's your interest at the end of the second year? Well, your money is worth 1 times your starting amount, which is in red now. So 1 times what's in red, plus your interest times what's in red, your starting amount for that year. And so at the end of the second year, you have what's in red multiplied by 1 plus I, which you can see is 1 plus I by 1 plus I, which is 1 plus I squared. So after 2 years, your money has now amounted to P into 1 plus I squared. And if we apply the same logic to 3 years, we'll find that the final amount or the future value is P into 1 plus I cubed. After 4 years, it's P into 1 plus I to the power of 4, etc. So in general, the future amount of your money is the present value times 1 plus I to the power of T, where T is the number of years. It could also, of course, be the number of months if your interest rate was in months, etc. And here it is again once more rearranged. If you divide across by 1 plus I to the power of T, your present value is your future value over 1 plus I to the power of T. So this formula here is called the compound interest formula. And whether you write it this way or this way, it's the same thing, just written a different way. Future value first or present value first over here. Now, why the need for two formulas? Well, generally speaking, when you're calculating savings, if you think about what savings are, you've got a present value that you've invested. You've invested your present value of your money, and it's gathering interest, and multiplied by 1 plus I to the power of t, and it becomes some future value. So that's when you use the first formula. You're thinking ahead to the future with savings. With loans, it's the reverse. You have borrowed money in the past, P. So the future value of your payments that you're paying off the loan with, this is F, for example. If you divide by 1 plus I to the power of t, it brings you back to the value of that payment on the day of the loan, which is P. We'll see more of that later when we're doing savings and loans schedules. And we'll also see that when you start paying regular amounts back into savings or into a loan, it gives you a geometric series in your formula as well. So we'll see all that shortly. So we can sum up everything really so far by the following graphic here, just to display what we're talking about. So the present value of our money, it gathers interest, multiplied by 1 plus I to the power of t, and it becomes F in the future. The future value or the final value is F. And vice versa. The future value, if you want to bring it back to the present, you divide by 1 plus I to the power of t. And you're back to where you started. So multiplication and division are inverse functions, and also obviously the division brings you back to where you started. So that's what an inverse function does. Next, we talk about depreciation. So when you get a question involving depreciation, you can think of that as simply, it's the same thing as working with a minus interest rate. So for example, if the depreciation rate of the value of something is 10%, it's going down 10% every year, for example, that's I is equal to 0.1. And what you do then is 1 minus I in your formula. So the only difference from the compound interest formula is it becomes a minus instead of a plus, and everything else is the same. So you go 1 minus I to the power of t, and that's your depreciation formula. So for example, 1 minus 0.1 would be 0.9 to the power of t. And that's how you work out your depreciation. Now, some definitions that you'll need to be aware of when you're working in financial maths. The interest rate on a loan is called the annual percentage rate, APR. But as far as you're concerned in the maths formula, it's just simply I. That's what you call I. For a savings, they tend to call it EAR, AER, or CAR, for example. And again, as far as you're concerned, that's not really important. What's important is that you call it I in the formula, in the compound interest formula. An annuity, well, that's basically where you're paying into some savings or investment account, and you're paying in equal amounts at the same time every month or every week or whatever it is. You're paying in regular amounts at regular intervals, basically. An amortized loan is the same for a loan. You're paying off regular amounts at a regular time when you're paying off your loan. That's an amortized loan. And then there's a bond. A bond is a certificate that you get from the government. You basically want to save your money with the government. So they give you a cert to say they have your money, and the terms and conditions basically, which is they'll pay you back with interest at certain intervals and so on. And you can also get a bond in a company. So it's the same idea. And finally, a mortgage is simply a loan on a property. It's a special loan, normally long-term, obviously, because it's a property and low interest. Now, some examples using the compound interest formula. So the first example here, let's take something simple to get started. You're going to invest 800 euros. And what will that amount to after 20 years at an interest rate of 2.5%? Well, the first thing you do is you take the interest rate to 2.5% and you convert that to a decimal, which is 0.025. And then you just fill in your formula. So the present value of your money is 800. I is now 0.025. And the time period for your loan or your savings, is 20 years. So you just fill in the formula and work it out on your calculator, and there's the answer, 1,310 euros and 90 cents. And the second example here, how many years will it take for 1,000 to amount to 2,000 at a rate of 6%? So in effect, you want to double your money. So again, fill in the formula. Your present value is 1,000. Your future value is 2,000. And you fill those in. You also know the interest rate, 6% is 0.06 as a decimal. So it's 1 plus 0.06, which is 1.06. Now the unknown this time is t, which is in the power, the time period of your savings. Divide both sides by 1,000 and you get 2,000 over 1,000 is 2 equals 1.06 to the power of t. Now the problem here is the quantity we want, which is t, is in the power. It's not that easy to get it down from the power. So we need to use a new technique, which is logs. We need to get the log of both sides. That's the method we use. So get the log of 2 is the log of 1.06 to the power of t. And the reason we use logs is because there's a rule of logs in your tables. And that rule says that the power can now come down in front. So that t up there, the t up there comes down here in front of the log. And that rule is in your tables, as I said. And now that's the t brought down, so we can solve for t now because we can just divide both sides by the log of 1.06. So t is now the log of 2 over the log of 1.06. And you get 11.9 years. And the last example, what interest rate would cause 500 euros to grow to 800 euros over 10 years? So again, just fill into the formula what you know. So we know the present value of our money, 500. We know the future value is 800. And we know the amount of time, it's 10 years. So fill all those in. Now we can divide across by 500, divide both sides by 500, and we get 800 over 500, which is 1.6, equals 1 plus I to the power of 10. Now, we need to get at this I here, that's what we're looking for, and the 10 is in the way. So there's another method now for getting rid of that 10. And that method is to take both sides to the power of 1/10, because the 1/10 is going to cancel the 10. And the reason for this is, here it is, 1/10 on both sides in right here. The reason for this is another rule in your tables. It's a rule of indices this time. And the rule says, if you have a to the power of p in a bracket to the power of q, well, the p and q multiply. You multiply the powers. And it's the same thing here. So the 10 in a bracket, the power of 10, and outside the bracket is 1/10. So you multiply those powers. So 10 by 1/10 cancels, and you're just left with 1 plus I. And the 1/10 is still over here, of course. And now to get I on its own, you just take the 1 across as a minus and you have your answer. So I is equal to 1.6 to the power of 1/10 minus 1. And that gives you 0.0481 on the calculator, or we'll say roughly 4.8%. And that's the last example, and that's the end of the introduction to financial maths.